Welcome to Spring LIB.
All right, we're given force, which is a vector of a sine kx in the I hat direction. So it just has the x component. We have to find u such that the initial condition is satisfied, which is that u at x equals 0 is 0. All right, so we know that u, the potential, is just the integral of f over the entire path length, over a path length. And so from 2 points, x1 and x2, basically. And so in this case, it would just be negative f dx over from x1 to x2. And so you have negative a. Well, let's just solve the indefinite integral, removing the x1 and x2, because that'll be easier to apply the boundary conditions, the initial conditions on. So you have negative a sine kx. Take the integral of that over dx, and we see that we can pull out the negative a. We can pull out the a, giving us sine kx inside the integral, because a is a constant, times dx. And so the integral of sine x over dx is just cosine x, but you also have you have sine kx. So so the k is pulled down to the denominator. So you have a times cosine kx over k, and that's going from a x1 to a x2. And so to account for that, we add an integration constant, c. So you have u of x is equal to negative a over k times cosine kx plus c. Okay, now we apply the boundary conditions or initial conditions. Apply initial conditions. So we're told that u of 0 is 0. So 0 equals negative a over k times cosine of 0, k times 0, cosine of 0 plus c. Okay. Cosine of 0 is 1, as we know. So we have that c minus a over k equals 0. So this obviously means that c is a over k. All right. So we have our integration constant. And so finally, we have our u, which is I forgot factor actually of negative 1, because when you're integrating sine x, you get a negative sign, so this will be a positive actually. And so you have c plus a over k, so c becomes negative a over k. Okay, so with that, we have u of x equals a over k cosine kx minus a over k. So we can take a over k common to get u of x equals a over k times cosine kx minus 1. And yep, and that's it.